All right, hello and welcome to Chem 100. We are going to continue lecturing. We're still in chapter 4. And on Thursday, we just completed, we ended, with a discussion of how to draw Lewis structures. And we're going to continue with that discussion today. Now, when it comes to drawing Lewis structures, so we spelled out our guidelines last week, or our steps. And step number one, for step number one, we total our electrons, our valence electrons. Step number two, so we pick a central atom. Step number three, we attach the remaining atoms to the central. Step number four, we complete octets. And step number five, we add our charges. I'm going to hold all questions about the oral exams for later, because we've got to move through our lecture material. We're still a little bit behind. But if you have questions, check out the post that I put in Canvas. All the information's there. Like I said, everything's on Canvas. If you have specific questions, you can email me. I'll answer them. But they're different dates for different sections. There's section 60 and 62, so that'll affect when you take it. But I publish both schedules. All the information's on Canvas. All right. So let's go ahead and continue. Let's draw the Lewis structure for formaldehyde, which is CH2O. Now, step number one is we have to total our electrons. Right, we have to total our electrons. Carbon, when you look at the periodic table, it is in the fourth column of the main group. So carbon will have 4 valence electrons. Hydrogen only has 1 valence electron. But the thing is, we have, I don't know why, I just did a superscript 2. Hydrogen has, or sorry, there are 2 hydrogens in this molecule. So both of them together bring a collective 2 valence electrons to our budget. And then oxygen has 6 valence electrons. So we have a total budget of 12 electrons to spend. Now, when it comes to picking the central atom, you want to select the atom that can make the most bonds, that likes to make the most bonds. And we said we could do this by looking at the unpaired electrons in our molecule. And so when you do, the Lewis dot structure for carbon has 4 unpaired electrons. Or here, actually. I want to do this part on another slide. So the Lewis dot structure for carbon has 4 unpaired electrons. The Lewis dot structure for hydrogen has 1 unpaired electron. And the Lewis dot structure for oxygen has 2 unpaired electrons. And what this means is that carbon, because you have 4 unpaired electrons, that tells you that under normal circumstances, carbon likes 4 bonds. Hydrogen likes 1 bond. And oxygen likes 2 bonds. That's because oxygen has 2 unpaired electrons, hydrogen has 1 unpaired electron, and carbon has 4. So we're going to select carbon for our central atom because it likes to make the greatest number of bonds. All right, so we're going to put carbon in the center. And that is step number 1. Actually, sorry, that's step number 2. We've picked our central atom. Step 3, we need to attach our remaining atoms. We have oxygen and 2 hydrogens to attach. So when we do, we have to spend electrons to make bonds, right? And there are 2 electrons in each bond. So this will cost us 2, 4, 6 electrons out of our budget. Leaving us with 6 electrons to spend. Now our hydrogens are content, right? Hydrogen wants to be like neon, so it wants access to 2 electrons. Oxygen, however, needs access to 8 electrons. It wants to be like neon. Now, when you look at oxygen as drawn in this structure, it only has 1 bond, so it only has access to 2. So to complete oxygen's octet, we need to give it 3 lone pairs, i.e. 6 more electrons. And we have 6 electrons in the budget, which is great, but now we're out. And this is where if you just blindly give everything dots without actually counting your electrons, it'll get you into trouble in problems like this. You'll notice that carbon, as drawn, has access to 3 bonds, right? So we've got 3 bonds. Which means that it has access to 6 electrons, but it needs 8. It needs 8 electrons. All right. It needs 8 electrons, but we have no more electrons in our budget. We have 0. If we had 2 more, we just give them to carbon, we'd be good to go. But we can't do that. All right. It looks like we are, and I'm putting this in quotes, missing 2 electrons. This is not uncommon when you're doing low structures. You'll run into situations like this where you're missing 2 electrons. What does that mean? That means when you're quote unquote missing 2, it means, so that's a problem, but the solution is always the same. To solve this problem, you need to create a double bond. And here's what I'm talking about. We have no more electrons in our pool of electrons to spend, so we can't just make 2 more electrons appear. But we could take 2 of the electrons on oxygen, and instead of making them a lone pair, we could use them to form a second bond between oxygen and carbon. All right? You'll notice that now, as drawn, oxygen has 2 bonds and 2 lone pairs. 2 bonds have 4 electrons. 2 lone pairs have 4 electrons. Oxygen has 8 electrons. And that's a complete octet. Now, as drawn, for carbon, carbon now has 4 bonds, which is 8 electrons. That's a full octet. So we have completed our octets. Oh, and skipping right over, we attached everything to the central. Forgot to check that off. All right. Whenever you run into this problem where you're missing 2 electrons, quote unquote missing 2, the way you solve this problem is make a double bond. And if you're wondering what is a double bond is that thing right there. It's 2 covalent bonds between 2 nuclei for a total of 4 electrons shared. All right? Let's do another example. Let's do another example. Sue, I don't know what section you're in. Let's save these questions till after lecture. All the information is in the syllabus or on Canvas, but right now we're working on lecture, so let's do that, and then afterwards I can answer questions. Okay. Oh, wait a minute. I'm so sorry. Snap. Did I? Okay, wait. Okay, so hang on. I'm so sorry. I moved the date of the exam. I'm like, what are you guys talking about? Your lecture. You're talking about not the oral exam, but the test, which was scheduled for today. Shoot. Okay, hang on. Okay. I don't know if anybody started it here. Give me 1 second here. I'm so sorry. That is my bad. I forgot that I moved the exam. Okay, Sue, I'm so sorry. Now I understand your question. I thought you were talking about the oral exam. Give me 1 second here. Yeah, there's apparently a lot of confusion going on. I think I bumped it to today, which now I'm lecturing, so if I did, I'm gonna do it on Thursday. I totally spaced this. Okay. Okay, okay. For anybody watching, okay, hang on, sorry. We were originally going to take exam 1 last week, but then I bumped it to today, but then I forgot, so I started lecturing. So I'm going to, exam 1 will be held, yeah. I'm moving it to Thursday. If you've already started it, you can stop. I'll reopen it. If you've already started it and you want to just take it, you totally can. You don't get to take it twice. There's still 1 attempt per person. So if you're taking it, just finish it. If you haven't started it, I will reopen it. I'll reopen it here. That is totally my bad. I'm so sorry for the confusion. I totally spaced it. Yeah. Don't worry. It says it closes tonight at 6:35. Yeah. This is true. For both sections. For Chem 100, 60, and 62. Yep, you guys all get another 48 hours to study because I totally forgot that I moved it to this date. I won't forget it's Thursday though. So I'm so sorry. I thought you were asking a question about the oral exam, but now I understand your urgency. You're like, no, I need to know right now. Do I need to take it now or not? And I apologize. Totally. Okay. So yes. So if you started it, you can finish it, and then on Thursday you can just watch today's stream. If you haven't started it yet, don't. After lecture, I'm gonna move the dates around so that it'll open and close next week. That is correct. Yes, Ariana. Yeah, next Thursday I won't do a YouTube stream. It'll just be take the exam, and then lab will be the oral exam for Thursday. Sue, thank you for being gracious. Also, thank you for bringing this to my awareness because, holy moly, I can still be a space cadet sometimes. Okay, well, how's that for a transition? I'm so sorry. Okay. I think what happened was I was so like focused on getting the oral exam written because that thing has taken a ton of work to give everybody like unique problems to do and all that stuff that I just totally forgot about the lecture exam. And so I just assumed like, oh, we're lecturing like normal. Yeah, holy moly. Here, where was, I'm just going to both sections. Lecture exam 1. just post this to each section. Yep. Just oral exams today. Okay. For Brianna, for section 62 they do. Okay. Well, is it possible to salvage the lecture? We're about to find out. Let's draw some more Lewis structures. Let's draw the Lewis structure for oxygen. All right, O2. Well, first we have to total our valence electrons. Oxygen, and we get this from the periodic table, has 6 valence electrons. And we have 2 of them. So again, that gives us a total of 12. 12 to spend. So that's our first step. We don't really have to pick a central atom because there is no central atom. There's just, 2 oxygens. So let's jump to step 3 and connect them. All right, now we've attached them. Now we got to fill out our octets. You'll notice that that oxygen, it doesn't matter which one because they're identical at this moment. There's 1 bond, so each oxygen has access to 2 electrons. So to complete the octet, we need to give oxygen 3 lone pairs, or one of these oxygens 3 lone pairs. And we can do it. Oh, whoa, hang on. Before I start giving out lone pairs, let's subtract our 2 for that bond we just made. There we go, 10 electrons left. And then the lone pairs will spend 6, leaving us with 4. Now you'll notice that we only have 4 electrons left. We're going to give these all to the second oxygen, but it will not be enough to complete this oxygen's octet. When you look at this oxygen right here, well, when you look at this guy, he's got 8 electrons around him, right? We've got, I need a little more space. 3 lone pairs, so that's 6. 1 bond, so that's 2. So this oxygen has 8. Full octet. Our second oxygen has 2 lone pairs, so that's 4 electrons. And 1 bond, which is 2 electrons. So at this moment in time, it only has 6 electrons. Problem is we're out of electrons in our budget, right? This is that same situation where you are missing 2 electrons, right? You're out 2 electrons. The way you solve this problem is you take a lone pair from the oxygen with a complete octet and you turn it into a second bond. Now look at what this does to our electron count for each oxygen. Our first oxygen has 2 lone pairs. So there's 4 electrons there. And 2 bonds. 4 electrons again, for a total of 8 electrons. That first oxygen still has access to 8 electrons. But now when we look at our second oxygen, it has 2 lone pairs, just like before. So that's 4 electrons. And it now has 2 bonds, which also contain 4 electrons. So now our second oxygen has access to 8 electrons, and we have completed our octet. All right, we're still ignoring step 5 because we're not dealing with ions yet. We'll get there by the end of today. So we're just holding off there for now. We totaled our valence electrons. Didn't have a central for this one, but we attached them, completed our octets. This is the Lewis structure for O2, the air we breathe. Yep. Carolina, that is correct. You can always rearrange your electrons after placing them on your molecule. All right, let's do another example. What about a molecule of N2? Well, nitrogen has 5 valence electrons because it is in the 5th column of the main group. We have 2 of them in play, giving us a total budget of 10 electrons. All right, again, no real central atom here because we only have 2 atoms present. And our first move is we need to attach them. So that will cost us, forming that bond will cost us 2 electrons, leaving us with 8. So at this point, we have totaled our electrons, picked a central atom, and attached the remaining atoms to the central. Now we got to complete some octets. Right now, each nitrogen has 1 bond, so it only has access to 2 electrons. So to complete our octet is going to require us to spend 6. It's 6 electrons to complete the octet of 1 nitrogen. Our problem is it'll take 6 to complete the octet of the second nitrogen, but we only have 2 electrons in our budget, so we can only give this nitrogen 1 lone pair. And this really is the problem, because you see this nitrogen has 1 lone pair and 1 bond. There are 2 electrons in a bond. There are 2 electrons in a lone pair. So it only has access to 4 electrons, and we are out. We have no more electrons left in our budget. All right? You're like, no problem. I know the double bond trick. Let's take a lone pair off of the first nitrogen and make them share. Right? Let's even this situation out. Notice what happens. This nitrogen still only has 1 lone pair, but now it has 2 bonds. That means that we have access to 4 electrons through our bonds. 2 plus 4 is 6. We still don't have 8 electrons. We're still missing 2. What do you do when you're missing electrons? You take a lone pair from one atom that's hugging them selfishly, and you make that atom share. You take that another lone pair from the hydrogen with a complete octet and turn it into a third bond, i.e. a triple bond. Now when you look, the second nitrogen has 3 bonds, so access to 6 electrons in those bonds, plus the 2 in its lone pair leaves it with 8 electrons. All right. So, wait, hang on 1 second. Okay. Okay, so that is the Lewis structure for N2 nitrogen. All right, now we've made it to a place where it's time to start talking about when do you need to worry about adding charges. All right, when does this fifth rule come into play? And it will only come into play when you draw the Lewis structure of an ion, specifically a polyatomic ion. All right, that is when you'll have to deal with this situation. All right, you're drawing the Lewis structure of a polyatomic ion. That's when you have to add charges right there at the end. So you actually have to deal with charges at the beginning when you total your valence electrons and at the end. And I'll show you how to do so in my next example. So let's draw the Lewis structure for hydroxide. All right. Now, we have to total our electrons. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron. Now we have to account for this charge. When you're drawing the Lewis structure for a charged species, it means that that structure either has more or fewer electrons than it should if it were neutral. Here, hydroxide has a charge of -1. That means that there's 1 more electron in this structure than there would be otherwise. And you have to take this into account when you total your valence electrons. If we have a charge of -1, that means that there is 1 extra electron in this structure. All right? 6 plus 1 plus 1 is 8. This gives us a total budget of 8 electrons. If we want to look at central atoms, hydrogen likes to make 1 bond. We can tell that from the Lewis dot structures. Oxygen likes to make 2 because it has 2 unpaired electrons. So we're going to select, well, I guess there is no central for this one since we only have 2 atoms. but we still have to attach them. All right, we attached our hydrogen to our oxygen, and that requires us to spend the first 2 electrons out of our budget. All right, now let's look at where we are. We have totaled our electrons. We've got a central. We've attached the remaining. Now we have to complete the octets. Hydrogen's totally happy. Hydrogen only ever wants access to 2 electrons. It wants to be like helium. Oxygen, on the other hand, needs 8, right? Just like most elements on the periodic table. And right now it only has access to 2 electrons in its bond. So it needs 6 electrons to have a full octet, and fortunately, we have 6 electrons in our budget. And that's it. Now, what do we do about step number 5? Add charges. Whatever the charge is on your molecule, you have to add it to the Lewis structure. And the way you do this is by placing a bracket around the Lewis structure and then writing the charge on the outside on the outside of the right bracket, superscripted. So this is now the answer. You have to bracket it, and then you put that charge, that -1 charge, superscripted outside the right bracket. That is the Lewis structure for hydroxide. All right, let's do another example. Let's draw the Lewis structure for hydronium. All right, let's handle a positive charge. First, we're going to total our electrons. Oxygen has 6. Hydrogen has 1, but we have 3 of them. So that'll bring 3 electrons to this party. And now how do we handle this positive charge? Well, a charge of +1 means you have 1 fewer electron than you should have, than you would have if it were neutral. So we actually, for this +1 charge, need to subtract 1 electron from our count. 6 + 3 - 1 is 8 electrons. We have a budget of 8 electrons. Given the choice between hydrogen and oxygen for a central, we're going to roll with oxygen. It likes to make more bonds. So oxygen will be our central atom. So we've totaled our valence, picked a central. Now we need to attach our remaining atoms to our central. So we have to attach, bond, our 3 H's. This is going to cost us 2 electrons each, right? 2, 4, 6. That's the last step. Let's not get ahead of ourselves. What we just did is we spent 6 electrons out of our 8 electron budget, leaving us with 2. You'll notice every hydrogen satisfied, right? It has 1 bond. Oxygen right now has 3 bonds. There's 2 electrons in each bond. So right now oxygen has access to 6 electrons. It wants 8. So we're going to spend our last 2 electrons to complete oxygen's octet. So we've attached remaining atoms. We've completed our octets. The last step, we need to add charges to the structure. To do so, we bracket the Lewis structure we've just drawn and add the charge superscripted outside the right bracket, and this charge is a +1. So this is the Lewis structure for hydronium. All right, let's do another example. Today is just going to be running through a ton of different Lewis structures. So let's do the Lewis structure. I'm going to throw a curveball. Let's draw the Lewis structure for nitrate, NO3. Nitrogen has 5 valence electrons. Oxygen has 6. We have 3 of them. 3 times 6 is 18. And now we have our -1 charge. That means there's 1 extra electron, 1 more electron than there should be. So our total electron count, let's see, 18 plus 1 is 19. 19 plus 5 is 24. This is our largest budget to date, 24 electrons. Next, we got to pick a central. Our choices are oxygen, whose Lewis dot structure has 2 unpaired electrons, and nitrogen, whose Lewis dot structure has 3. We know the more unpaired electrons, the more bonds it likes to make. So we're going to roll with nitrogen as our central atom. Next, we need to attach our remaining atoms to nitrogen. This is going to cost us 2, 4, 6 electrons to do. So 24 minus 6 is 18. All right. Now we got to complete some octets, right? Oxygen has access to 2 electrons. It wants 8. So it needs 6 more. 2, 4, 6, 8, 10. What am I doing? 2, 4, 6, 8. 8 electrons. That'll cost us 6 out of the budget. Leaving us with 12. Our next oxygen also needs 6 more electrons. We have it in the budget, so let's go ahead and spend them. Our final oxygen also needs 6 electrons, and we have 6 electrons exactly in the budget. The problem is now we're out. Now we're out, and nitrogen only has 3 bonds, which means nitrogen has access to 6 electrons, and it needs a full octet just like every oxygen. Not a problem. What do you do when you're down 2 electrons? You make a double bond. So we're going to take a lone pair. For many oxygen, it does not matter which one you pick. You could do yellow, violet, or green. I'm going to do violet. I have no idea why. We take a lone pair off of one of our oxygens, any one of our oxygens. We make a double bond between that oxygen and nitrogen. And now nitrogen has 4 bonds, which means it has 8 electrons. Octet rule has been completed. Our last step, don't forget we're dealing with an ion. So now we have to add our charges. We throw a bracket around our entire Lewis structure and then put our charge for nitrogen superscripted outside the right bracket. All right. So let's do another one. Let's do maybe somewhere between 2 and 3 more. Let's do carbonate next. Charge of -2. Charge of -2. Let's total our valence electrons. Carbon has 4 valence electrons. Oxygen has 6, but we're dealing with 3 of them. 3 times 6 is 18. And now we have a charge of -2. That means we have 2 extra electrons in this structure. So we need to add 2 to our electron count, giving us a total electron count of 24. So now we've totaled. All right. When it comes to picking a central atom, carbon has 4 unpaired electrons in its Lewis dot structure. Oxygen has 2. So we're going to select carbon as our central, and we're going to attach our oxygens to our central atom, spending 2, 4, 6 electrons. All right, so now we have 18 electrons to spend. We need to start completing octets. Oh, we did step 3, now we're in step 4. We got to spend 6 to complete our first oxygen's octet. We have to spend 6 to complete our second oxygen's octet. And our final 6 we will spend on our final oxygen's octet. All right. Our only problem is carbon right now has 3 bonds, which means it has access to 6 electrons. It needs access to 8. So since we're missing 2, right, 2 electrons, we have no electrons left in our budget. We're going to take a lone pair. Could be from any one of these carbons. I'm going to pick the yellow one. And we're going to make a second bond between that oxygen and carbon. So now all octets are complete. And now we need to add our charges. So we slap a bracket and we add our charge superscripted outside of the right bracket. And that is the Lewis structure for carbonate. Okay. There is one last twist to this tale of drawing Lewis structures. Whoa, throwing my stylus. One last twist that I have to share with you. And that is the last twist is breaking the octet rule. I want to talk to you for a minute about breaking the octet rule. bring this back in just a second. First, let's talk about less than 8. Is it possible to have less than 8 electrons? The answer is yes. They're very rare, but they can. Boron is notorious for boron often has 6 valence electrons, such as the Lewis structure for BH3. In this Lewis structure, there are only 3 bonds. There are only 6 electrons around boron. All right, so that's one instance of having less than 8. There is a second famous instance, which is NO, which is a gas. If you draw this Lewis structure out, it'll look like this. In this structure, nitrogen has only 7 electrons. All right, only 7 electrons. The reason why I'm pointing out, these are exceptions to the rule. They're very, very rare. And these compounds, because they break the octet rule, because they have less than 8 electrons, are very unstable. So they're very reactive. They do all sorts of things. Borane actually burns green. I've actually seen a borane fire before, and it looks like Maleficent is right about to show up. The reason why I'm pointing these out to you, I'm not going to test you on either of these. I'm not going to test you on compounds that have fewer than 8 electrons. Sorry, I'm not going to test you on compounds with atoms that have fewer than 8 electrons. So you don't have to worry about them. The reason why I'm bringing them up is so that you're aware that they exist. If you come across them, you're like, oh yeah, that's that weird example. But I won't actually put this on an exam, so you're fine. What I will put on the exam, what will be covered on the exam, are atoms that can have more than 8 electrons. These guys you got to be aware of. Now, to show you which atoms can have more than 8 electrons, I'm going to use the periodic table. The atoms that can break the octet rule by having more than 8 electrons are third period, and lower. You're like, wait a minute, third period and lower. Where is that? Well, here's the third period. Everything on the third period and down can break the octet rule. And you might be looking at that and going, Josh, that's most of the periodic table. There's 118 elements, and you're telling me that 10 of them, 11 and up, can break the octet rule? Oh. You're telling me that elements 11 and up are allowed to break the octet rule? Why is this thing a rule if it's only a minority of the periodic table? The answer to that question is twofold. First, just because these elements can break the octet rule by having more than 8 electrons doesn't mean that they will. All right, so just because they can doesn't mean they will. They have the capacity to, but they usually don't. They usually still follow it anyway, even though they don't have to. So that's one reason. The second reason why the octet rule is important, or I said one. Second reason why the octet rule is important is look at the atoms that always obey the octet rule. Carbon, oxygen, hydrogen, nitrogen. The majority of biological systems are made up of these 4 elements. Almost all of you, the overwhelming majority of your entire body, of all the trees, of all the animals, of all living things are made up of these 4 elements, and these 4 elements never break the octet rule. So that's another reason why it's so important, is because all of our biochemistry, I can't say all, nearly all, 90+ percentile of our biochemistry is governed, is ruled by the octet rule. So that's another reason why it's so important, is because even though elements that must always obey the octet rule are in the minority, those minor elements are the majority of all biological systems. So that's another reason why the octet rule is crazy important. Here's where this matters for us. Whenever you have an element that is on the 3rd period or lower, so here, let me. Elements on or beneath the 3rd period elements on or beneath the 3rd period make the best central atoms. And that is why I'm bringing this up to you today. If an element is on the 3rd period or lower, it will make the best central atom, because you always want the element that can make the most bonds for your central atom. And if it's allowed to break the octet rule, it can make more than 4 bonds. So always pick 3rd period elements or lower when it comes to selecting a central atom. And we'll close out with a couple more examples. All right, so let's draw the Lewis structure for sulfate, for example. Well, first we want to total our electron count. Sulfur, if you're unaware, is in the 6th column of the main group. So it'll have 6 valence electrons. Oxygen has 6, but we have 4 of them in this molecule, so that's 24. And we've got a charge of -2, which means we have 2 extra electrons in the mix, giving us a total of 32 electrons. 32. Now, when it comes to picking, so total valence electrons. When it comes to picking our central atom, sulfur is on the 3rd period. So that is going to be our central because it's allowed to break the octet rule if it wants to. All right, now I'm going to zero out the periodic table so we can have some room to work. But we're going to pick sulfur as our central. And now we need to attach our other atoms. So attach oxygen, all 4 of our oxygens, and this is going to cost 2, 4, 6, 8. 8 electrons out of our budget. (32 minus 8 is 24. Next, okay. Well, let's just do it one step at a time. So we have oxygen needs 6 more electrons to complete its octet. So let's give it 3 lone pairs and take 6 out of our budget. That'll leave us with 18. Our next oxygen also needs 6 electrons. We have it. So let's give our next oxygen 3 lone pairs. That'll leave us with 12. Our next oxygen also needs 6. We have 6 in the budget. Or we have 12 in the budget. So that leaves us with 6. Let's give this oxygen 3 lone pairs. And then our final oxygen needs 6 more electrons, and look at that. We have exactly 6 in our budget. We don't need to make any double bonds or anything. We do, so let's look at this. We've attached everything. We've completed our octets. We now need to add charges. So we throw a big old bracket around our molecule of sulfate. And we had a charge outside, superscripted, outside the right bracket of -2. This is our Lewis structure for sulfate. All right. Let's do at least one more example. Let's do the polyatomic ion, which we haven't learned. Bromate. Bromate. Well, bromine is in the 7th column of the periodic table, or of the main group. So it has 7 valence electrons. Oxygen, as we know, has 6. We've got 3, so that'll be 18. 18 electrons. We have a charge of -1. That charge of -1 adds one extra electron to the mix, giving us a total of, let's see, 7 plus 1 is 8. 8 plus 8 is 6. Carry 1, so 26 electrons are in our budget. Now we have to select a central atom. Third period is here. Everything below this can break the octet rule. Bromine is below the third period, right, which starts here. So we are going to select bromine as our central atom. Keeping track of our steps here. We've totaled our valence, we've picked our central. Let's attach our other atoms. Now we have 3 oxygens to attach, so this is going to cost us 6 electrons. Six electrons. Next, we need to complete some octets, right? Our first oxygen needs 6. We have that in spades. 20 minus 6 is 14. Our next oxygen also needs 6, which we do have. 14 minus 6 is 8. So let's add 3 lone pairs here. Our third oxygen needs 6, which we do have in our budget. There are 2 electrons remaining. And look at bromine. In this structure, bromine has 3 bonds. That's access to 6 electrons. It wants 8. So it needs 2 more electrons, and we have 2 more electrons in the budget. So that is our Lewis structure, well, with completed octets. Let's not forget that because we're dealing with an ion, we have to add charges. We need to put this entire thing in a bracket, then put our charge superscripted outside the right bracket. So that is the Lewis structure for bromate. All right, let's do one more, then we'll call it a night, and I will start prepping for round 1 of our oral exams, which begin at 7, by the way. All right, last example. Let's go out with a bang. Let's do the Lewis structure for phosphate. -3 charge. Phosphorus has 5 valence electrons. We get this from the periodic table. Oxygen has 6. We have 4 of them. So it's 24. Now our charge, which is -3, means that there are 3 extra electrons in this structure that wouldn't normally be there if it were neutral. So we need to add 3 electrons. Five plus 3 is 8. 8 plus 24 is 32. So at this moment, we have totaled our electrons. When it comes to picking our central atom, you guessed it, phosphorus is on the third period. So it's going to be our central atom. Yes. Carolina, that is exactly correct. And that is often the case with elements on the third period or below. Totally, Blake. After this example, I'll hit you up with an answer to your question. Elements that are on the third period or below are allowed to break the octet rule, but they don't have to. And often they don't. They actually like kind of following it, but every once in a while you'll see it spring up where they don't. Okay. So we selected phosphorus for our central atom. Next, we need to attach our 4 oxygens. 2, 4, 6, 8. This is going to cost us 8 electrons. Yeah, dude, of course. 32 minus 8 is 24. Now we got to start filling out our octets. Our first oxygen needs 6 electrons, and we have that. 24 minus 6 is 18. There's 1, 2, 3, 4, 5, 6 to that oxygen. Our next oxygen also needs 6, and it is in our budget. So we allocate them accordingly. 1, 2, 3, 4, 5, 6. Our third oxygen needs 6 electrons. We've got 12 in the budget at the moment. Whoops. 12 minus 6 is 6. Our fourth and final oxygen also needs 6 electrons, and we have 6 in the budget. So that will round out our octet. Our final step, so we've got these two, and this only applies to ions, which phosphate is. We have to add our charge, and our charge will always be superscripted outside the right bracket. So that has a charge of -3. And that is the Lewis structure for phosphate. We're going to go ahead and call lecture there. It's a natural stopping point. Yes, they totally can. Carolina, and actually, I won't do this one. So I did hydronium earlier. So I did do one example of a positive ion, though the negative ones are more common. That's why I was doing more negatives. But if you wanted to give a positive one for a whirl, try doing the Lewis structure for ammonia. If you want another example of a positively charged polyatomic ion. And if you want to know how to handle it, see how I did H3O plus, which was earlier this lecture. But I spent most of my time doing negative ions because there's way more negatively charged polyatomic ions than positively charged ones. All right. Anytime. Anytime whatsoever. All right, so that brings lecture to a close. I think Blake had a question about exam one. I got a few minutes, or 5, I guess. I looked at the clock, which I will have to run at 6:35 just so I can start gearing up. I've got a couple things to prep for the oral exam, which occupied so much of my brain hole that I forgot about the lecture exam. And my apologies. Okay, Blake. Oops. Okay, Blake, I will get back to you on through email. Yeah, Aaron, it's all in the Canvas post I made today. There's a Zoom link there. There's a link to the spreadsheet that you'll be able to find your time slot. Totally, Blake. Yeah, we'll work something out. I'm sorry that it kicked you, and yeah, I'll be in touch. Probably not tonight, honestly, because I'm going to be doing oral exam after oral exam, but I'll shoot you an email tomorrow. Totally, and we'll sort it out. Don't worry about it. Yeah, Aaron. Yeah, it's in the Canvas post. There's the Zoom link. You join the meeting. Everybody will be in the wait room, and then I will add one person at a time. And you'll have 13 minutes to answer the questions, and that'll be it. It's not going to be too strenuous. I think it'll be pretty chill, or at least that was my intention. We'll see how it goes. I've never done an oral exam in person, let alone online. So, we'll see how this thing goes. I'm going to. So, Aaron, you know how like I'm streaming this whiteboard canvas, whiteboard, this Photoshop canvas. You're gonna see this in the Zoom meeting, and then I'm going to put like problem 1 up on the page. You figure it out. You tell me what the answer is, and then you move to the next one, and then I'll put the next problem up on the page and do that for 13 minutes or fewer. So I will give you, so Juliana, what you'll see here is, and it's not going to be handwritten, it's going to be typed, so it'll look more like this. You'll see, like, so it'll be, when you log in, it'll be like blank, and it'll be like, oh hey, let's get started. Problem 1. And then I put it up on the thing. Yeah, totally. You figured it out. Tell me what the answer is. I will enter it on my end, And that's that. Totally. So yeah, you don't have to. You won't. And the thing is, I've already written these all out, so you won't have to wait for me to type it. You won't have to wait for me to write it. I'll just you'll log in, you'll join the Zoom meeting, and everything will be invisible, and I'll be like, all right, let's start. Here's problem 1, and I'll throw problem 1 on there, and then I'll erase that and throw problem 2. So it shouldn't be too shabby. All right, I'm gonna go. There's just a couple finishing touches I need to put on the exam. So we're starting at 7. I'll enable the Zoom meeting a few minutes before so that everybody can like get on, join the waiting room, and it should well, it'll be an experiment. I've never done one of these before, so we'll see how it goes. Thanks, dudes, for showing up. Sorry for the exam confusion. We'll iron out some of the deets for some of the stuff that went wrong over email tomorrow, and I'll catch you in lecture on Thursday. I won't, because you'll be taking an exam, so I won't be lecturing.